Hello and welcome back. So today I want to start looking at phase lock loops or PLL circuits. Now these are quite common building blocks in modern electronics, seeing widespread use on the one side in digital electronics for things like clock synchronization and multiplication, but also used in analog electronics for things like AM or FM or even digital encoding, demodulation. Now, since the topic of PLLs is quite vast and complex, today I will be focusing only on the phase detector part. So I want to look at ways of building the phase detector in digital PLLs using logic gates. So if you're curious, then keep watching. So to start things off, the phase lock loop is quite a complex circuit built from other smaller little circuits. So we got our input signal that is fed into the phase detector, so this is the first block, and depending on the phase difference between this signal and another signal, the phase detector will produce an output that, depending on how the phase detector is built, can contain all sorts of harmonics and high frequency content. So a low pass filter is used to only keep a DC value, or at least a slow moving AC signal. This signal is then passed into a voltage controlled oscillator, so an oscillator whose output frequency is dependent on this control voltage, and then the output of this oscillator is fed back into the phase detector either directly or through a divide by n counter. So depending on what you're trying to do, you either want the output of the oscillator to be exactly the same as your input signal, or you want it to be a multiple of it. And if you do want that, then you will be using your divider counter to provide a lower frequency that is the same as your input. Finally, the two signals, the input and the one from the oscillator, are compared and the loop is closed. So the loop will stabilize when the two input signals have, first of all, the same frequency, and regarding phase, depending on how the phase detector is built, it will either lock on a phase difference of 0 degrees or some other value. Now, to get a better understanding of how this phase detector works, let's have a closer look at the signals that it will be trying to compare. So what I have here is two signals in 4 cases. So on the one side, with a 0 degrees phase shift, both signals look exactly the same, have the exact same timings. Then we have the 180 degrees phase shift. So here the two signals are one inverted in reference to the other. And the last case we want to look at is the 90 and 270 degrees phase shift. So you can look at this as a plus 90 and a minus 90 phase shift. So here the two signals are shifted in reference to the input signal. On the one side 90 degrees forward, and on the other side in green 90 degrees backwards. So our phase detector is a circuit that should give a different response in all of these cases, and it should also give a proportional response in reference to just how much phase shift we actually have. And as with all good circuits, there's multiple variants. So the first thing to look at is the type 1 phase detector that can be implemented with exclusive OR logic gates. So now let's see what sort of outputs we get if we pass our two input signals through the type 1 detector, or in other words, through an exclusive OR type gate. So in the first case, when we have 0 phase degrees between the two signals, well, we get nothing. So we have an output of 0. Because in the case when both input signals are low, we get a low output, and also in the case when both input signals are high, we get a low output. At the other end, with 180 degrees phase difference, we have always a high output, because we have a low input and high input leads to a high output, and then in the other case we have a high input and a low input, which again leads to a high output. So with 180 degrees we have a constantly high output signal. Now in the middle case, with either 90 degrees plus or 90 degrees minus, we get something like this. So we do get the case in which when one input is low and the other is high, leading to a high output. We get the case in which both are low, which leads to a low output. We then have the opposite case of the first input being high, second low, so a high output, and when both inputs are high. So again, a low output. And now the reason why I put in the same graph both the plus 90 and the minus 90 degree phase shift is because they both give the same output. Now the two are inverted, but if you pass these two signals through a low pass filter, so to average them out, the average value will be exactly the same in both cases. So if we consider low 0 volts and high 1 volt, then the average of both these signals is 0.5. And this shows us one of the main problems of the type 1 detector. It's a phase detector that can give a clear difference between 0 degrees and 180 degrees, but for the intermediate values, it will not be sure if the phase is lagging or leading. So we get exactly the same response for plus 90 or minus 90 degrees. So this is a type of phase detector that will give a minimum value at 0 degrees. If you start to increase the phase difference, it will increase up until 180 degrees. When the board falls down, it will increase the value up until 180 degrees when it's at maximum. And then if you increase the phase more, then it will start to decrease again up until 360 degrees or again 0. So to quickly try this circuit out, I prepared an LT-Spice simulation. So what we have here are two input signals, the type 1 phase detector, so an exclusive OR type logic gate, and then a low pass filter just to average out the response so that we can get a DC value. Now regarding the input signals, I have two signals with the same frequency, so we have a 2 millisecond period with a 1 millisecond on time, so 50% duty cycle. But the difference between the two signals is that one of them has this PD, which is the time delay parameter, and I'll be giving this various values between 0 and 2, which correspond to 0 to 360 of phase shift. So now if we run the circuit and just focus on the output, we see that for our 5 cases, we have, well, 3 main lines. So let's see which is which. The first line in green that goes on the bottom, so it always stays at 0, corresponds to the case in which our phase delay is 0. So at 0 degrees, we have a 0 output voltage. Then if I move through the graphs, so using my arrow keys, I went up. The second graph is the blue one, which corresponds to our 90 degrees phase shift. Next line, the red one, which is at the maximum value, corresponds to a time delay of 1 millisecond, so 180 degrees. And then afterwards, at 1.5, we're again at 0.5, and finally at 360, the pink one is again at 0. So we can clearly see our output going from 0 phase degrees, 0 volts output, through the middle value at 90 degrees, up to the maximum value at 180, and then it goes back down to 0. So now, if we don't want this sort of response, we want a clearly different response for each phase difference between 0 and 360, we can go for a more complicated circuit, the type 2 phase detector. So now let's have a quick look at that. So one implementation of a type 2 phase detector looks something like this. So it's a bit more complicated than a simple XOR gate, but I'll walk you through it. So first of all, our signals pass through D-type flip-flops. So these are logic gates that will trigger on edges. Then the outputs of these pass through an AND gate, which resets them. But they also pass through a couple switches, one that pulls the output high and one that pulls the output low. And now, depending on how you want to build your phase detector, you can have the output left floating when both switches are off, or add a resistor divider to set up center voltage. So now, to get a better understanding of how this works, let's look at how it reacts to some signals. So first case, we have two signals, S1 and S2, where S2 is behind S1, so this one triggers first. So when we get the rising edge on S2, it will trigger the output of the lower flip-flop, so Q2 goes high, and it stays high up until the point when S1 also has its rising edge, which triggers Q1 to be high. But since both of these are high, then the AND gate output is high, so it resets the circuit. So we just get a small glitch here on Q1, and then both the outputs are low. and they stay low up until the next rising edge, which again is on S2. So again we get a pulse on Q2, and when we get our rising edge on S1, it resets. Otherwise, if we have the other case, where S1 comes first and S2 afterwards, then we trigger Q1, so S1 had the first rising edge, Q1 becomes high, and it stays high up until the point when S2 gets its rising edge, so Q2 becomes high, and since both are high, then the AND gate resets the two circuits, and then they both become low. So in this case, we get pulses on Q1. And depending on the phase difference between the two, so the larger the phase difference between S2 and S1, then the larger the pulse on Q2 will be. Or in the other case, the larger the difference between S1 and S2, the larger the pulse width on Q1 will be. So with this circuit, we have three different cases. On the one side, if both of the signals are perfectly in phase, so zero phase difference, the output is set at the middle of the supply, so with these resistors at half the supply voltage. If S1 is behind S2, like in this case, then we will get positive pulses going into the upper switch, so the output will be higher and higher depending on the phase shift. Or if S2 is first, then we will get pulses on Q2 going into the lower switch, so we'll get a lower voltage than the half voltage. So with this sort of phase detector, we get a clear difference for any phase difference between 0 and 360. But also different output from 0 to minus 360. Now we can get a clearer picture of how the circuit works using the circuit simulator. So what I have here is a circuit that we just talked about, with the difference that I added some transistors instead of the switches, and because one of the transistors is an NPN and the other is a PNP, the PNP is connected to the inverted output of the logic gate of the D flip-flop, and on the AND gate I also added the time delay between when the inputs are both high and the output becomes high, and this is needed to provide a certain delay between when the rising edge occurs on the input pulses and when the flip-flop turns off. So this thing is needed to be built into the circuit. Same as before, I added the low-pass filter on the output so we can see a DC value. And as signals to test, we have quite a bunch of them. So first of all, the reference signal is delayed by 2 milliseconds. And then we have our second signal that has a delay between 0, so minus 360 degrees from our reference, up to 2, so in phase, and then up to 4 to have 360 degrees. So we have a span of 720 degrees of phase difference. So if we run this thing and we look at the output, we see quite a lot of colors. So now let's see which is which. So the first signal, time delay of 0, so minus 360 degrees, which is the same as in phase. We have our middle output. Then we jump down, so this is our minus 270 degrees, minus 180, minus 90. Again, in phase, we are in the middle. And then the next, the plus 90, is going above. So this is the plus 90, then we have the plus 180, plus 270, and then at plus 300, we're again in the middle. So we can see that positive phase differences are higher than the 0 degrees value, and negative phase differences are lower than the 0 degrees value. But at this point you might be wondering, well, minus 270 and plus 90 is really the same thing, isn't it? Well, it is, but this is not really a problem, because this circuit has another extra feature built in. And we can see that if we look at what sort of response we get with the two phase detectors when signals of different frequencies are inserted. And for that, I prepared this setup. So here we have the same circuits as before. The only difference is that the second signal we're comparing our reference to, rather than having a certain delay, it has a different period and frequency. So the values I've given for the secondary signal range from 1 millisecond of period, so half the frequency of our reference, 2 milliseconds, same frequency, same phase, 3 milliseconds, which is 3/3 of the initial frequency, and finally 4 milliseconds, which is double that of the initial frequency. So if we run this circuit and see what happens, first of all with the type 1 phase detector, and we quickly check the outputs. So we see that the case in which we had half the frequency has a response at about 500 millivolts. So this was the same as 90 degrees of phase shift. Then the case in which the two signals are in phase is down here at 0. And then the other two cases are again at around 500 millivolts. So this sort of phase detector doesn't give a clear answer regarding the frequency of the secondary signal. So if it's higher or lower. It's different than 0 degrees, but nothing else can really be made out from this. Now if we turn to our type 2 phase detector and look at the output, we see a slightly different picture. So here on the bottom, we have the case in which we had half the frequency. Then right in the middle we have the case with exactly the same frequency. And then above we have the two cases in which we had higher frequency. So 3 halves and the double frequency. So the type 2 phase detector is also called a phase frequency detector because it gives a different response if the secondary signal is at the lower frequency or at the higher frequency than the reference signal. So we can see that clearly here that when we had higher frequencies we had higher values, when we had lower frequencies we had lower values. Finally, let's look at the two types of phase comparator on a practical circuit. Now to keep things simple, I will be using the CD4046 type IC. Now the nice thing about this component is that it has all the building blocks necessary for a phase lock loop, but especially it has the two types of comparators built in, and we can access the outputs of each of these at the same time. So what I built is a circuit in which I'm inputting two signals into the comparator inputs from the signal generator, and then the outputs I'm filtering using a low-pass filter and then outputting towards the oscilloscope. So you can see what happens on the two types of phase detectors. I would also like to mention that for the type 2 phase detector, I also added this resistor divider to provide a half voltage point. And to test things out, I prepared this setup. So what I have here is my signal generator, the analog discovery. I have my little board with the 4046 IC, which I'm supplying from my power supply. And then the two outputs are connected to the oscilloscope. So channel 1 is the type 1 phase detector, channel 2 is the type 2 detector. And at the moment, the signals that I'm inputting are 5 kHz signals, and they're in sync at 0 degrees. So you can see that the response of the two types of phase detectors, type 1 is outputting a low value, close to 0. Type 2 is outputting a value of about 2.6 volts, so half the supply voltage. So now if we start to increase the phase difference, say we go to 90, we see both outputs go to higher values, so as expected. We can go even higher to 180. Again, both outputs increase. Now if we go to 270, we can see that the type 1 phase detector dropped in output. So we see this behavior that after 180 degrees the output starts to decrease rather than continue increasing, whereas the type 2 still increases. And if we go to 360, well, we're back where we started. So again, 0 phase degrees, we're at the reference. Next thing to look at is what happens when we apply signals of different frequencies to the phase detectors. And for that, I prepared a setup in which one channel has a constant 5 kHz signal, whereas the other sweeps from 4.9 up to 5.1 kHz in a span of about 5 seconds. So if we run this setup and we have a look at what's going on, let's just focus on the type 1 for the moment. So we can see that we have an oscillation appearing. The detector is detecting a phase that goes constantly up and down. But what's interesting about this oscillation is that it's at the frequency of the difference between the two input signals. So basically what this circuit is also doing is outputting the frequency difference of the two input signals. So in case they're at different frequencies, you will get the output frequency here. But you don't get a clearer answer on whether this frequency difference is one way or the other. So if your reference signal is higher or lower frequency than the input signal. On the other hand, if we turn now to the type 2 phase detector, we see that we have two clear regions in which the signal appears, either on the upper half or the lower half. So based on whether the frequency difference is positive or negative, we are in one half or the other of the output. So this is a clear indication of how the phase frequency detector part works. So we have a completely different response depending on what the relationship between the two frequencies is. So now, depending on your needs, you can use either the type 1 or the type 2 phase detector. Although the type 2 has some more interesting features, it's more complicated and this makes it work a bit slower, but it's also more susceptible to noise. So in case you get all sorts of extra transitions in there, then the output will be corrupted. The type 1, on the other hand, is much simpler, will work much faster, and you can also build it in an analog version, not just in a digital form. But that is a topic for a different time. For now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.